Alright everybody, this is part of going back over chapter 5, which is the exponential function and logarithms. So last time we talked about some of the different properties of exponentials and exponents in general, and so now we're going to go ahead and actually build up the exponential function. So our old functions and the things that we're most used to are things like functions like polynomials, maybe functions that involve square roots, things like that. What we did at the start of the semester was we talked about rational functions, like that. Right, and so these were all old ways of making functions, things that we could graph, things that we could talk about properties of. And in all of these, the variables were being raised to various powers. So now what's going to be happening is the exponential function, the variable is the power. Right, so now we're going to be talking about functions like, let's call it k of x equals 2 to the x. So now what's going to happen is you're going to be changing the inputs, and each new input is going to give you a new exponent for the base. And so let me go ahead and quickly label this. This is the base, right, and that's the exponent. So let's go ahead and just make a table for 2 to the x. So whenever you're dealing with a new function, it helps to try some values, try to find some values that are easy to compute, possibly make a graph of it. So here's our input, here is 2 to the x. I'm going to go ahead and plug in -1, 0, 1, and 2. 2 to the -1, 2 to the 0, 2 to the 1, 2 squared. Okay. So a couple of things. I'm going to start bottom up because they're more familiar to us. 2 squared, right? That's 2 times 2, which is 4. 2 to the 1 is just 2. 2 to the 0 is 1. 2 to the -1, one of the things that we should know is that when you have a negative exponent, you take the base, make the exponent positive, and move it to the other side of the fraction it's on. So if you have a negative exponent and it's in the numerator, which in this case 2 to the -1 is in the numerator of 2 to the -1 over 1, you would move it down into the denominator and make the exponent positive. So a couple of quick examples, let me go ahead and put up here, like 3 to the -2 would be 1 over 3 squared, 1 over 4 to the -1. You switch which side of the fraction it's on, so since it's in the denominator, it moves up to the numerator, and so it becomes 1 times 4 to the +1. See how we can do that? Things are allowed to move up or down, right? And remember, if you're wondering whether or not something is in a fraction, you can always put it over 1, and now it's part of a fraction. And so 2 to the 1 we said before was 2, so this just becomes a half. So let's talk about some of the things that we can notice. Going from a half to 1 is like multiplying by 2. Going from 1 to 2 is like multiplying by 2. Going from 2 to 4 is like multiplying by 2. What about going in the other direction? Going from 4 to 2 is like multiplying by a half. Multiplying by a half. And multiplying by a half. So each time When we multiplied by 2, it was because we were adding 1 to the input. And each time we divide by a half, it's like subtracting 1 from the input. So going backwards is dividing by 2, going forwards is multiplying by 2. Let's go ahead and try to plot this. So if I add my points to the graph, remember when I plugged in 0 I got 1, so that gives me a y-intercept of 1. When I plugged in -1 I got 1/2. When I plug in 1 I got 2, and when I plug in 2 I get 4. So here are a couple of points. If I want, I could go backwards, and a half of a half is a quarter. And I can't go forwards on this graph because I've run out of space, but let me go ahead and connect my points. And roughly speaking, here, let me see if I can draw that a little smoother. Roughly speaking, here's the graph of 2 to the x. A couple of things we can notice is if we keep going in this direction, we're going to keep dividing by 2. So what do we have? We have a half, a quarter, an eighth, a 16th, and so on. These numbers are getting smaller and smaller, but they're never going to be negative. So as x goes to -infinity, 2 to the x is going to get closer and closer to 0. In this direction, we keep doubling, right? Remember, going in that direction is like halving, and going in this direction is like doubling. So if every time we double, we're going to keep getting bigger, right? 1, 2, 4, 8. So as we move in this direction, 2 to the x is going to be getting bigger without bound. So that's going to go to infinity. So here's an example of something we didn't have when we had polynomials and rational functions. This has a horizontal asymptote, right, of y equals 0, but it's only in one direction. It's only towards -infinity. There is no horizontal asymptote on the right. It increases without bound. Something really important is that it goes through the point 0, 1. And the other things that are important are that this function is smooth, it's continuous, and that's really it. So we have an important point, we have what the function does on the left and on the right, and we have the fact that it's smooth and continuous. So let's talk about one other important fact. This is big. If you have the same base, so if you have a to the x equal to a to the y, then x has to equal y. And let's go back and look at our graph. And let's imagine that I'm just going to draw some horizontal lines here. We don't even have to imagine, I'll draw some. Here's a horizontal line. Here's a different horizontal line. And what you can actually see happening on these horizontal lines is that they intersect the graph, and they intersect the graph only once. See right there? See right there? Each of those horizontal lines only touches my graph exactly once. And if we go back to this property, right, the point at which it touches, right, so here's some number, this is the number 2, right, this represents 2, and so here is where 2 to the x is 2. What we're saying is that if you have some numbers x and y that when you raise the base to them give you the same answer, right? So if 2 to some power was 2 and 2 to some different power was 2, well, then it turns out that they actually have to be the same power. And you can see that because each of our lines is only hitting once. And so this is really neat because it allows us to solve some equations. So for example, if I tell you 2 cubed equals 2 to the x, then you know that x has to be 3. Right? It's the only power of 2 that is the same as 2 cubed, which is 8. Well, that's really silly. That's simple. What if I tell you that 2 cubed equals 2 to the 2x minus 1? Well, again, we can extract from that that 3 has to equal 2x minus 1, and we can solve and get that x has to equal 2. Let's try another example. 2 to the x minus 5 equals 2 to the 2x plus 1. Again, that means that x minus 5 has to equal 2x plus 1. And so what we get from this is that moving our x over and moving our 1 over, x has to equal negative 6. And if you check, that'll give you 2 to the negative 11 equals 2 to the negative 11. And so we're all good. So these are some really basic examples of questions that you can answer now using this new fact. And sometimes the questions are going to hide the fact that you can use this. So let me give you an example of how we could hide it. Suppose I ask you, when is 4 to the x equal to 2 to the x plus 3? And you may say to yourself, Matt, 4 and 2 are not the same base. See, back here in the property, we have an a and another a, right? So we don't have 2 and 4 with the same base. But in the back of your head, little alarm should be going off, and you should be thinking that 4 equals 2 squared. And those little alarms are trying to tell you that you could actually rewrite this as the same base. Step 1 is to write 4 as 2 squared, and be very careful and leave that x outside of the parentheses, equals 2 to the x plus 3. Remember, we did some rules of exponents, and we said if you do one exponent followed by another, you can just multiply them. So this becomes 2 to the 2x equals 2 to the x plus 3. And from our previous property, a to the x equals a to the y means x equals y. Tells us then that 2x equals x plus 3, which is the same as x equals 3. And you can check, 4 cubed is the same as 2 to the 6th. Let's try one more. 4 to the x equals 8 to the x minus 1. Now here's where you have to, again, in the back of your head, you should be thinking 4 is 2 squared and 8 is 2 cubed. Now we didn't have that 4 to some power was 8, but we do have that 4 and 8 are actually powers of the same base. And so we're going to write 4 as 2 squared to the x, and we're going to write 8 to the x minus 1 as 2 cubed to the x minus 1. Now here's where it's really, really important that you just use parentheses. Although the fact that we're going to get 2 to the 2x on the left is totally apparent, on the right you might be tempted to write 2 to the 3x minus 1 if you didn't use parentheses properly. That's bad. What you really want to do is you want to multiply all of x minus 1 by 3. So we're going to get 2 to the 3 times x minus 1 which is 2 to the 3x minus 3. And so we get 2x equals 3x minus 3, which tells us that x has to equal 3. And that tells us that 4 cubed is the same thing as 8 squared. And you can check that and it's true. So some of the most basic properties of the exponential function were discussed today. We started by saying that instead of using variables as bases and having various exponents applied to them, what we're going to do now is use the variable as the power. We made a chart, and we noticed that an increase of 1 is the same as multiplying by the base, and a decrease of 1 in our inputs is the same as dividing by the base. We did a basic graph and talked about some of the properties. And then we talked about a way to start solving some of the equations involving exponents. We used the fact that if a to the x is a to the y, then x has to equal y. So we solved a couple of basic equations, and that's the end of the lesson. I'll see you in class. Make sure you do the homework. Have a good day.